Hi, welcome back. This is our 6th lesson of the second module. We're going to talk about nonlinear programming and the language method, Lagrange method with the slack variables. Today, we're back to the second hour, looks like. Again, we talk about Lagrange multiply method and deal with the nonlinear problem. That's different from the 5th hour, the nonlinear. It is also different from the second lesson. We got the in-equation constraint. In the second lesson, you only have equation constraint. You have this, but you don't have that. So today, you got the full scope of the optimization. That's how I put it. You can deal with the most general problems with linear or nonlinear functions with both equation constraint and the in-equation constraint. That will be a little bit more difficult, you're going to see. So as an outline, first I give you the canonical form. That means how you're going to write the equation in the standard way. Then you can plug into the MATLAB formulas or the method. And then we're going to introduce two different ways to solve it. The first is the graphic method, and the second is the analytic method with this Lagrange multiply. And then we're going to bring you the third method. Use the MATLAB command called the fminicom function. All right, let's start from an example to show you why it's so important to introduce this in-equation constraint. Now, start from today, I can bring you some kind of research problem. Now, this is one nice application to the AUV path optimization. You know, A is autonomous underwater vehicle. If you have an underwater vehicle, you might have to plan the shortest path from a point A to the point B. Now, between the paths, you might have some kind of rock or a sinking boat blocked your way. So how you are going to navigate from this point to here to build the shortest path? Well, that's an optimization problem. Then what kind of constraint you could have? Of course, you have the mechanical constraint. That means your pitching angle have a limit. You cannot pitch vertically probably. And your yawing angle could have a range in each time. So that's a mechanical constraint. Typically, it's less than a certain degree. You cannot say you have to be equal 30 degrees. Usually, so it's less than 30 degrees. That's an in-equation. Well, other constraint is the geometric constraint. For example, you wanted to walk around this rock. You need to make sure you have a safe distance between the rock and the vehicle. So again, your constraint is the distance bigger or equal a certain distance, let's say 2 meters. So naturally, you understand the constraint does not have the form of equation. Instead, most of them are in equation. That's why without the lesson today, your knowledge is still very limited and could not solve all application problems, all optimization problems. Now, I hope you got the bigger picture. In lesson 2, you got the nonlinear part, but you don't have inequation part. In the lesson 5, you got both inequation and the equation, but your function have to be linear, means they're all first degree. But today, let's start from an example like this. Look at this example. So in this example, that's obviously a nonlinear function. What you call it? Quadratic, right? Of two variables. And you have a constraint equation. This one's linear. That's a nonlinear. That's a circle. And you also have two of the constraint in equation. That's linear. The x1 plus x2 less or equal than 7. But this one is not linear. You have this x1 minus 0.25 x squared less equal than 0. And you also have those upper boundary and the lower boundaries. So that is the full complexity, even it's a simple example. So let's back into the canonical form. How should we write those problems? Well, to solve an application problem, the step 1, you identify all the design variable. Sometimes we also call it control variable. And that's the variables x, y, z for the AUV navigation problem. And each variable have an upper limit and the lower limit. For example, the lower limit typically is bigger than 0. If it's in application, rarely you're gonna find them negative. Upper limit could be the speed or is less than 20 feet per second, something like that. So you get the design variable. The variable has a low bound. That's why I use the L. And then up bound. That's the U. And then, of course, any optimization problem, you have an objective function. I use the capital X. That means you got the n variables. The third part is nothing new. You learned in the second lesson. You got all the constraint equations. That's equation, equal, equal, equal. What's new is here. You got the constraint in equations. That the G group less than B1, B2, BL could be 1, 2, could be any number of the in equations. So the canonical form has 4 components. The design variables with the upper limit and the lower limit, the objective function, and the constraint equations, constraint in equations. And that pretty much covers all optimization problem. And this field usually is called operation theory. You know, if you go to the financing field, economic field, that's the typical equation you're going to deal with. Okay, back to this example. Let's identify the design variable is x1, x2, and the lower limit is 0, upper limit is 10, see here, and the same here. That's the first item. Second item, the objective function is here. It's quadratic. That's the second. Third, constraint equation, you have two of them. Fourth, the constraint in equation, you get the two of them. All right, that's the all four components. Let's look at the solution. It was easy because it's a 2D. I can sketch it. The two blue curves are the constraint equation. See, the first one is the straight line. You look, the blue line. This is the straight line. That's H1. The second one is a circle. And you see this circle? That's the blue line. Since those are the equation, in our case, the two equations have only 2 points are the solutions because they are in 2D. In other words, you only either give this solution or that solution. That's your choice. But how about the in equation? They're made by this two red line, but there's for the first line need to be the inside. Let me draw a little bit. The inside is this domain. That's the physical domain defined by the first in equation for the straight line. The second one is a parabola. Look at the second one here. Need to be less than 0. That means it need to be in the x1 side, and then should be defined by this domain, this piece. Let me use another color. Should be here. So your physical domain is between this to here and here. That's the physical domain. And you only have 2 points, 1 point here, 1 point here. Of course, that point is the only solution here. Let me erase it just for the mess. Now, the 2 points is one here and the one here. Obviously, this is out of the domain. The triangle physical domain, this is out. That does not count. That's the only solution. Well, you look at those green curve. Those are called the contour curve. Contour curve. Sometimes we call it a level curve. In all this green line, your objective function in here all equal 10, 20, 30, 40. That's why it's called the level curve. So we need to minimize. That means the smaller, the better. But in our case, you have no choice. That's the point of your solution. So what is the point? The x is 1. Let me get a little up. We maybe can see it. Okay, that's 2 is halfway, yeah, that's 1. And the y is 6. So it's 1, 6. And this looks like a touched 20, but it's not true. The minimum is 19. That's the easy way. And by the way, you got this function, join line, join circle in the MATLAB in your homework folder. You can just apply it, change the function. They can draw this kind of lines for you. Okay, that is very intuitive, right? You have the constraint equation, give you the points and the lines, and the constraint in equation basically give you those kind of physical domain. Feasible domain. And then you use this contour curve to find the minimum.